Hi class, as promised, I'm going to work out the problems in the worksheet 2. So the first problem says to calculate the molarity of chloride ion in 245 milliliters of a solution that contains 23.4 grams of barium chloride. So we already know that molarity is the moles of solute per liters of solution. So I need to convert the grams of barium chloride to moles of barium chloride, and the molar mass of barium chloride is 208.23 grams per mole. So I'm going to go ahead and divide the 23.4 grams by the molar mass. So we have 208.23 grams per mole, and that is, I'll put that into my calculator, 208.23. So that we have 0.112 moles of barium chloride. Okay, now they want to know the molarity of the chloride ion. So 1 mole of barium chloride contains 1 mole of barium and 2 moles of chloride ion. So when we dissolve that, it's going to dissolve into, again, 1 mole of barium ion and 2 moles of chloride ion. So the number of moles of chloride ion would be 2 times 0.112 moles. So that would be 0.224 moles of chloride ion. So now all we need to do is calculate the molarity. We have 245 milliliters of solution. When we convert that to liters, we just divide it by 1,000. And now we go ahead and calculate the molarity of the solution. We have 0.224 moles of barium or chloride ion divided by 0.245 liters. And so 0.224 divided by 0.245 liters, and that gives me a molarity of 0.914 molar in chloride ion. Okay. Number 2, what are the respective concentrations in molarity of iron 3 and iodide afforded by dissolving 0.2 moles of iron 3 iodide in water and diluting to 725 milliliters. Well, 725 milliliters is the same as 0.725 liters. And again, the iron 3 iodide, okay, that's going to give us 1 mole of iron plus 3 moles of iodine. Okay, so this would be iron plus 3. Okay, so those are the ions that we're going to have. So we can we'll first do the molarity of the iron 3 ion. So iron 3, the molarity would be 0.2 moles divided by 0.725 liters, and that'd be 0.2 divided by 0.725, and that'd be 0.276 molar. Now for the iodide ion, for every 1 mole of iron 3 iodide is going to have 3 moles of iodide ions. So that's going to be 3 times 0.2 2 moles. So we're going to have 0.6 moles of iodine. So for the iodide ion, we're going to have 0.6 moles divided by 0.725 liters. So 0.6 divided by 0.725, and that'll be 0.828 molar in iodide. So that'll be 0.828 molar in iodide ion. Okay. Number 3, what volume of 0.25 molar nitric acid is required to neutralize a solution prepared by dissolving 17.5 grams of sodium hydroxide in 350 milliliters of water? So we need to convert the grams of sodium hydroxide into moles, and then we determine the molarity. We have 350 milliliters. That's the same as 0.35 liters. So the molar mass of the sodium hydroxide, let's see, sodium hydroxide, we can just calculate that. That's 39.997 grams per mole. So the molar mass of sodium hydroxide is 39.997 grams per mole. So we'll go ahead, and we have 17.5 grams of sodium hydroxide. We'll go ahead and divide that by its molar mass, which is 39.997 grams. So 17.5 divided by 997, that's 0.43, 0.438 moles of sodium hydroxide. Okay, so we have our balanced chemical equation here. So what we need to do is determine the number of moles this should be molar, I'm sorry, I was going to say, we need to determine the number of moles of sodium hydroxide. So to do that, remember, molarity is moles of solute over liters of solution. So we multiply the molarity times the volume to determine the number of moles. So we have 0.438 moles per liter, and the volume is 0.35 liters. Whoops. So 0.438 times 0.35, that's 0.153, 0.153 moles of sodium hydroxide. Okay, so it wants to know what volume of nitric acid is required to complete this reaction. We know from the reaction we have a 1-to-1 mole ratio of nitric acid to sodium hydroxide. So that means that we have 0.153 moles of sodium hydroxide, and that is going to react. We have a 1-to-1 mole ratio of sodium hydroxide to nitric acid. So that means we're going to have 0.153 moles of nitric acid react. And so it wants to know the volume of the 0.25 molar nitric acid. Well, we know the molarity of the nitric acid, and we know the number of moles. We got it right down here. So we need to solve this for volume. So the volume is going to be equal to the number of moles over the molarity. So we have 0.153 moles of nitric acid divided by the molarity, which is 0.25 molar. I'll write that as moles per liter. Okay, so let's see, we're going to have 0.153 divided by 0.25, and I get 0.612 liters for this one. Okay, so I get 0.612 liters for this problem here. Okay, what volume in milliliters of a concentrated solution of sodium hydroxide must be diluted to 200 milliliters to make 880 or 0.880 molar of sodium hydroxide? So this is a dilution, so we use our M1V1 equals M2V2. So our M1 is 6 molar, and they want to know what volume. So we're looking for V1, and our M2 is 0.880 molar. We'll multiply that by 200 milliliters. Okay, so V1 is going to equal 0.88 molar times 200 milliliters divided by 6 molar. Our molarities cancel out, and we'll be left with milliliters. So that's 0.880 times 200 divided by 6, and I get 29.3 milliliters. Okay. Here they want to know how many milliliters of 6 molar nitric acid solution are needed to make 0.25 liters of a 3.5 molar solution. Again, this is M1V1 equals M2V2, and we're looking for V1. So V1 is M2V2 over M1. So V1 is equal to, V2 is 3.5 molar, and we will multiply that by 0.25 liters, and then we'll multiply this by 6 molar. Molar cancels, and we're left with 3.5 times 0.25 divided by 6, and that should be, that's equal to 0.146 liters. They want it in milliliters, so you multiply this by 1,000, and that's 146 milliliters. Okay. Number 6, how many grams of potassium nitrate are needed to make 250 milliliters of solution that is 0.135 molar? So we know again that the molarity is the moles of solute over liters of solution. So what we need to do is solve for the number of moles. We have the molarity, we have the volume, and we need to solve for the number of moles. 250 milliliters is 0.25 liters. So the number of moles is going to be the molarity times the volume, and that's going to be 0.135 molar times 0.25 liters, and that's going to be 0.135 times 0.25, and that's going to be 0.03375 moles of potassium nitrate. So now we need we have to convert the moles to grams. We use the molar mass of the potassium nitrate. So again, we can calculate that, and the molar mass is 101.1032 grams per mole. So we have 0.03375 moles, and we go ahead and multiply that by its molar mass, 101.1032 grams, and that would be equal to I get 3.41 grams. Okay. This one here, it asks how many milliliters of 0.3 molar lithium sulfide are needed to react with 25 milliliters of 0.315 molar silver nitrate. So first thing we need to do is make sure that our equation is balanced. We have 2 silvers and we have 1. Okay, so everything, this is balanced. And so first we'll determine the number of moles of silver nitrate. And we do that by multiplying the volume in liters. So this is 0.025 liters times the molarity. So we have 0.025 liters times 0.315 molar, or we'll just make that moles per liter. We see the liters cancel. And we have 0.025 times 0.315, and I end up with 0.007875 moles of silver nitrate. Now what I need to do is use my mole ratios from the chemical equation to get from silver nitrate to lithium sulfide. So I have 0.007875 moles of silver nitrate, and from my equation I see that 2 moles of silver nitrate will react with 1 mole of lithium sulfide. So we'll go ahead and put that in the calculator. So what I have is 0.00394 moles of lithium sulfide. And what they want to know is how many milliliters would be needed. Well, we have the molarity and we have the number of moles. Remember, molarity is moles per volume in liters, and we need to know the volume. So liters is going to be equal to the number of moles over the molarity So we have 0.00394 moles. We'll divide that by 0.3 molar, or 3 moles per liters. This cancels out. And we have 0.00394. Oops, where did that come from? 394 divided by 0.3. And that is 0.0131 liters, but we need to be in milliliters, so we divide this by 1,000, or multiply it by 1,000. That's 13.1 milliliters. Okay, number 8. What volume of a 0.54 molar potassium hydroxide solution contains 15.5 grams of potassium hydroxide? So first thing we need to do is convert the grams of the potassium hydroxide to moles. And so the molar mass of potassium hydroxide is 56.1056 grams per mole. So I have 15.5 grams of potassium hydroxide, and we're converting from grams to moles, so I'll go ahead and divide it by the molar mass. And let's see, 15.5 divided by 56.1056, and I get 0.276 moles of potassium hydroxide. So they want to know the volume. So again, molarity is moles of solute, in this case the potassium hydroxide, over liters of solution. So we need to solve for the volume. So the volume is going to be moles over molarity. So we have 0.276 moles divided by the molarity, which is 0.540. That's moles per liter. Moles cancel. We're left in liters. So 0.276. I don't know where this pi came from. 0.276 divided by 0.54. And that 0.5111 liters. If they wanted milliliters, we would just multiply this by 1,000. That'd be 511 milliliters. Okay. All right, number 9. How many grams of barium chloride are formed when 35 milliliters of 0.00237 molar barium hydroxide reacts with excess chlorine gas? So this is in excess. So let's go ahead and determine the moles of barium chloride. That's the volume in liters. That's 0.035 liters times the molarity. That's 0.00237 molar. And that's 0.035 times 237, and I get 8.29 times 10, 1, 2, 3, 4, 5 to the negative 5 moles of barium hydroxide. So now we make sure our equation is balanced, and it is. Okay. And so they want to know how many grams of barium chloride are formed. So we have 8.29 times 10 to the negative 5 moles of barium hydroxide. And from our chemical equation, we see that 2 moles of barium hydroxide will produce 1 mole of barium chloride. So let's see, we'll divide that by 2. That's 4.15 times 10, 1, 2, 3, 4, to the negative 5 moles of barium chloride. So now we just need to convert moles to grams. So we have 4.15 times 10 to the negative 5 moles of barium chloride. And we did the molar mass of barium chloride. We did that up here. Barium chloride has a molar mass of 208.23 grams. So 208.23 grams. 208.23 grams per mole. And that's 208.23. So I get 8.64 or 8.64 times 10 to the negative 3 grams of barium chloride is produced. So you can see with all of these problems, we're doing them the same way as we did all the stoichiometry problems. The only difference is, you know, like here, we were given the volume and the molarity of the barium hydroxide. So we needed to determine the number of moles and then use our mole ratios from the balanced chemical equation. Number 10. When 50 milliliters of a 1 molar solution of iron 3 nitrate are mixed with 50 milliliters of 1 molar solution of sodium hydroxide, a precipitate forms. So that precipitate is iron 3 hydroxide. So how many moles of this precipitate is formed? So again, first thing, make sure that your equation is balanced, and it is. So we have a balanced equation. So let's go ahead and determine the number of moles of each of these. And so we multiply the volume in liters times the molarity of the solution. And this is just 0.05 moles of the iron 3 nitrate, and we're also going to have 0.05 moles of the sodium hydroxide, right? Because we have 50 milliliters, which is 0.05 liters times the 1 mole. Okay, so we have this. So what we need to do is we need to find our limiting reactant here. So let's go ahead and start with the 0.05 moles of iron 3 nitrate. And you know, if we were to react all of this, we go to the equation, 1 mole of iron 3 nitrate will produce 1 mole of the iron 3 hydroxide. So we have 1 mole of iron 3 hydroxide, 1 mole of iron 3 nitrate. So we have 0.05 moles of iron 3 hydroxide. And then we'll go ahead and do the same with the moles of sodium hydroxide. So we have 0.05 moles of sodium hydroxide. And from our chemical equation, 3 moles of the sodium hydroxide will produce 1 mole, will produce 1 mole of the iron 3 hydroxide. So 0.05 divided by 3, and that's going to give us 0.01667 moles of iron 3 hydroxide. So obviously our limiting reactant here is the sodium hydroxide, so it doesn't matter. You know, if I have this much sodium hydroxide, I could have, you know, 10,000 moles of iron 3 nitrate. The most that I can make would be 0.01667 moles of iron 3 hydroxide. So yeah, I think they just wanted to know how many moles of precipitate is formed, and that would be 0.01. So it'd be 0.0167 moles of iron 3 hydroxide. I noticed in the answer key they say it says 0.05 moles, and that is not correct. It is 0.0167 moles. Okay, I think they I don't know why it's incorrect in the answer key, but it is. So yeah, this one here, this should be 0.0167 moles. Okay, so I hope this helps. Again, if you have any questions, please either send me an email or stop by office hours on Monday or Tuesday. But I want you guys to do well on the exam. I mean, you know, you guys got the videos, you have your textbook, you should be reading that, and you should also be doing the practice problems in the textbook. So everybody have a great evening, and I'll see everybody Tuesday in the exam, the Zoom. So have a great night. Bye-bye.